Hello everyone, welcome to another video. Today we're going to be talking about linear search algorithm and a bunch of little aspects when we talk about maintaining and testing your code as a programmer. All right, let's talk about linear search, pseudocode, errors, testing, and documentation. Okay. So to start off with, to give a nice little introduction to everything that we're going to talk about today, we're going to start talking about the linear search algorithm. So we're going to see how a linear search algorithm is written in pseudocode. So in the top two lines there, I have described that array is an array of values, so it has collections of values inside from left to right, and it is indexable, as in we can go to a location of where that value is located with integer index starting at 0, with the very first items being index of 0. And target is just a variable that represents a value that we're trying to search in the array. And the linear searches purpose goes as following. We're going to start from the very beginning of the array, which is a collection of multiple data values, and we're just going to go from the beginning until the end until we either find the value that we're looking for and return its location index, or we reach the end having not found our target and we're going to return a value of -1, or in this case we're going to output that it does not exist. Okay. So we're going to set this I variable to 0 because our very first item in our array is at location 0, and we're going to say, well, we're going to loop everything that's indented here. We're going to loop while the value of I is less than this size, or the length of the array, less than how many values we have. Okay, if we had 5 values inside an array, right, the length of the array is 5, but the indexes goes at 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. Even though there's 5 values in that array, since we count from 0 and every beginning item starts at an index of 0, we go 0, 1, 2, 3, 4. Okay, so we complete our code as long as this I value is less than the length of my array, which is 5, and our final value will be 4 because we have 5 items. Right? Because when our I value is either equal to the length or greater than the length of the array, we shouldn't loop anymore because our condition says the following. We're going to loop while our I value is less than the length of the array. So we're going to say if that array at location I is equivalent to the target. So when we're talking about equivalent, we can put double equal signs there. Then we're going to output that the target is located at this index location and end if. Okay. Whereas if we don't find it, we increase the I by 1 and we loop over and over and over again. And this code actually should say that it should exit the loop if the target was found. And then we end the loop whether we have reached the end or we were able to find the target value that we're looking for at location I. And then we're going to say, well, after the loop was over, if I is somehow either greater than or equal to the length of the array, that means that we didn't find it. So we're going to write this output message of target does not exist in the array. So whatever that value target was, we're going to write this sentence out after that says whatever the value was, space, does not exist in the array, and that would be the end of our linear search. So what is linear search? Linear search is an exhaustive searching algorithm that looks for the first occurrence of a given target value from the beginning of the collection to the end. And its goal is to return the location of where the target value exists. And if not found, it is often really to know that it will output a value of -1. So if we now then consider, well, we don't know what our array is going to be composed of, right? We don't know how many values it will have. We don't know if it's going to shuffle or not. So if we were to generalize different cases, like whether if we got the best possible case for a linear search or worst possible case or the average case, and we can see what those performances are. Well, the best case scenario for a linear search would be that the target that we're looking for was the very first value. So we didn't even need to look at the array. It exists at index of 0, so we find it right away. The worst case scenario, there are two possible worst case scenario. The target itself does not even exist within the array. So we have to look at every single value from index 0 of the array to all the way to the end of the array, and to find out that the target that we were looking for did not exist in the array, or the target is the very last value after we have compared every single value in that array. We got to all the way to the end, then we found the value that we're looking for. However, in average scenarios, we are expected to find our target value somewhere in the middle if we're given that kind of suboptimal scenarios with running a linear search. Okay, so let's talk about some weaknesses then. Why is linear search weak? Well, it can't return multiple indexes if the target occurs multiple times. It is supposed to exit the very first time it finds a value and ignores any other values that it could have found afterwards. The performance of linear search slows down dramatically as the dataset increases and increases. When you have a dataset that only has 10 values, you, at worst case, only have to do 10 different comparisons. But if that dataset contains 1 billion data points, then you have to do 1 billion data comparisons to, at worst case, to see if your target exists or not. Okay. Number 3, this is this is an algorithm that it is independent from previous searches. There is no learning, there is no optimization, there is no improvement happening when you run this algorithm multiple times, because there is no, I would say, there is no elegant nor sophisticated way that it learns from previous executions to track and remember where certain values were. And number 4, there are no early termination unless the target is found, right? Like, for example, if the data set is sorted and we've reached a point where the target value cannot exist. So let's say I'm looking for value 6, okay? I'm looking for value 6 in my array, and I know that my values went 1, 2, 7, 10, 12. Well, as soon as I got to 7, and knowing that my data set is sorted, I don't need to search the rest of the data set anymore, because 6 cannot exist above 7, knowing that our data set is sorted. So if when we got to this value 7, we could technically exit our algorithm so that it doesn't waste computer resources to continue to look on for values, but a linear search wouldn't do that. So why do I talk about linear search today? Because algorithms are the pillars of computer science, and we're going to be doing a lot more deep dives into them. And when we rank algorithms. Algorithms are ranked based on their worst case performance. Whether it be like it takes up a very long time to complete, or it takes up a lot of memory to complete the problem. And those are the two things that we worry about when we do algorithmic design. And that will be one of the main focuses of this course. To design algorithms, we must learn what pseudocode is. So pseudocode is a description of an algorithm without using any specific programming language. Pseudocode will mix common programming language conventions and the English language, okay? And this is important in software design because it is readable by everyone. As long as you have a basic understanding of programming, most people will be able to read pseudocode and then translate that into whatever programming language that they're comfortable in, right? And also, it focuses on logic rather than nuances of a programming language. So you don't need to wait until it is interpreted. You don't need to wait until it's compiled. You can literally write pseudocode on paper, so you can even be independently away from a computer as well. Therefore, it is faster design in pseudocode than in programming languages because you're not reliant on and using the proper rules of a programming language. That means we can create faster prototypes where we can detect early errors onwards. So let's talk about errors. Errors happen often, and as a programmer, you want to embrace your errors because errors tell you where you went wrong, and so that you should be able to fix them. And errors are a really good way to learn good habits when you're programming and to know what you did wrong. So I want to say this phrase here: on the pooping is carpet dog. Everything is spelled properly, but we have no idea what that means. That would be an error, right? You could be the best memorized programmer who knows every single key word and important functions that exist in a programming language, but if you don't use it in proper order and or properly in general, you're gonna get gibberish like so. So, in the English language, we would have to write this previous sentence into something like the dog is pooping on the carpet. Now it is fully following the rules of the English language. And then we have another example here. The dog ate my homework yesterday. So this kind of makes sense, but you see glaring errors where it can be fixed to the dog ate my homework yesterday. And this is an example of syntax error, a mistake in code that violates the programming language's rules and prevents it from executing correctly. So this is the number one error that you want to avoid by writing proper code following the proper conventions and rules that the programming language will provide. So in this situation here, we had no capitalization of the first word, no period to end the sentence. We misspelled homework. We even used a wrong tense when we should have said ate, not eat. Therefore, even programming languages will have a similar types of rules where we have to use it properly, where capitalizations will matter, spelling will matter, and that will make a big difference when you're coding as well. Okay, so in this example here, on the above, I have print hello world. It looks pretty nice, but print does not actually exist. It's actually missing a T for print. So there you get a name print is not defined. You get an error. It looks scary when you get an error message, but it's something that will tell you that you got something wrong. So it is a really nice learning tool to know what to fix. In this situation here, right, I have started a quotation mark and I didn't end my quotation mark for my text, which should end after my exclamation mark. So you always want to make sure if you start a bracket, end the bracket, start a quotation mark, end the quotation mark. You want to be tracking that as you program. Now, moving on to more types of error, I want to read you this little story. A programmer gets sent to the store by his wife. His wife says, get a gallon of milk, and if they have eggs, get a dozen. The programmer returns home with 12 gallons of milk. So this is called a semantic error. So unlike a syntax error, the code faithfully follows the code that was given. The computer follows the code that was given. However, you as a programmer didn't intend for the behavior of the program. You were actually expecting something else, but the program output is something way different than what you anticipated. So you created a semantic error. The program was successfully able to execute code from top to bottom without any errors, but the expected result was wrong. That means something went wrong along the way, even though everything went well in terms of execution. So for example, here, if I have A is equal to apple, and it says if A is equivalent to watermelon or wintermelon, it is going to print melon. Else, it is going to print it is not a melon. We expect that it's going to print it is not a melon because A is not watermelon or wintermelon. Unfortunately, in computer languages, especially the use of an OR is not a value combination. We're not really checking in this scenario where we're saying if A is either watermelon or wintermelon. This is actually not what it's doing, but rather we are saying if A is equal to watermelon or this right side value logic evaluates to true, because OR is a logic combiner, not multiple value combiner. And we will learn what that means later on. So this unfortunate code actually prints out that it is a melon because apple, no matter what the value of A was, even though if it's not watermelon, but the right side will always evaluate to true, making this entire if statement true. And it prints it is a melon. Now I have a silly picture here that is my brother-in-law's cat. And we can obviously tell it's a cat, but I've labeled it as dog. This is another type of semantic error and another error called value. A cat is not a dog. And in the same sense, when a program is expecting certain types of data in a situation, and if we provide the wrong type of data, it is going to output a value error. For example, I said, hey, I want to turn this string, this textual message of a dog, into an integer. Well, it's impossible. It's going to tell me it's a value error. There is no equivalent integers for dog. So if we have errors, we also want to be testing our code. We write tests to test if our application works fine, but since tests are also code, we must test the test and to see if it is testing properly. And this is one of the most difficult point of programming because we need to test our main code, but we also need to know if our test is working properly. So often we write tests for those as well. And this entire field is called quality assurance. Quality assurance, or QA, is any systematic process used to determine if a product or service meets the quality standards. And this is most often a very important department in any programming, developing, engineering firm. And there are different ways to test. First is a unit test. We test individual components or functions of a code, and then we do an integration test. We put multiple components and functions together and see if they work together. And then once we have all those different functions and components coded, we do a system test. We put everything together and see if the entire application is running properly. Then after that, we have that entire application running. We write acceptance tests to make sure that the business that hired the software team wrote a proper application that passes all the requirements that the business asked for. And then we also do performance tests because you might have not tested with multiple people using the app at once, and you might have only tested it by yourself while nobody else was using that application. So it's important to do performance tests as well. And there are different ways to test. You can do manual, automatic. Manual is more a human testing the application, and advantages are it's flexible, it's user focused, and there's quick feedback because there's a literal person testing the app, but it wastes a lot of time. It takes a lot of resources because you're taking away a potential developer who could be working on new features, but they're stuck on testing. And also, humans are prone to errors and being inconsistent. Whereas if you have automatic testing, it is extremely fast, efficient, it is consistent, you can scale it, and it's reusable. Once you have a really good automatic testing system, you can use that same test over and over and over again. However, once again, it is costly to make. Since it's automatic and automation, you need to have code that run these tests, and you have to make sure these tests are running well. So you have to test the test and all that stuff, and you get into an infinite cycle. So how do you generate test cases for unit tests? Because unit tests are the simplest tests that you can start off with when you're starting to code. And first type of test is called positive test, where you provide valid inputs that should provide correct results. So if I had an adding function, if I provided the value 2, 3, we're expecting 5 because 2 is a valid input, 3 is a valid input, and we're expecting a valid input of 5. We can also check for negative tests where we provide invalid inputs that should provide an error. So we're trying to actually break our unit test. So if I were to ask this add function to add 2 and tomato together, it should be an error. If I asked a dividing function, hey, like could you divide 69 by 0, there should be a division error because you can't divide anything by 0. Then there are boundary tests as well. We're providing inputs that are at the edge of the input boundaries. For example, if we had a password length function that checks how long the password is, if we gave it a lower threshold of 8 and an extremely high 16 threshold for maximum length, we should be able to run this code no problem. Whereas edge tests, we want to provide like very unusual, extreme, very rare cases to the function to see how it behaves. So example, if we had a function that checks if the email is valid, we can provide this weird email address with 2 valid email domains and leading spaces leading and trailing the word itself, and to see how it handles that type of situation. And then lastly, we can have performance tests where we provide a lot of inputs or gigantic inputs so that we can test the speed and the memory usage of a given function as well. And then lastly, we have documentation. Documentation is really important when we talk and explain what we have coded, or you read a bunch of documentation to learn how to use third-party libraries throughout coding, because that is a very important aspect of programming as well. So, documentation are written text or illustration that accompanies computer software or is embedded in the source code somewhere as well. So, you can actually launch a documentation function to see some of the documentations that are written for the program itself. And really, the documentation's purpose is to help programmers understand how the code works, how to use it, how to maintain it. It provides simplicity when using the code such that you don't need to guess what a feature does or a function does in that code. You can make it more accessible for others by having a nicely written documentation so that they can read up on it. And often you'll see tutorials, guide, and installation instructions so that you can use such code in your own program. So if I wrote a little linear search algorithm here, right, I have a little documentation here that where it just says the purpose, types of argument this function is expecting, and the value that we're expected to return when we find or not find a target within the array. And it might look like that. Okay, so when we document a code in Python, you can write single lines of human readable notes. We often use the hashtag symbol right in front of it, where Python knows that it is reserved as a comment so that the interpreter can ignore it. And we also have triple quotation mark system where you create a doc string, where often these are reserved for describing what a function is, method, subclass, or module is. So they have their own purposes as well. So today we talked about linear search, pseudocode, errors, testing, and documentation, and those are all very, very important parts of computer science. And I hope that this was a really good introduction to what we'll be doing in the future when we start coding ourselves. And as always, thank you for watching and stay classy.